white tissue on leaves. That was a layer of leaves.
Well, it wasn't the brightest thing I ever do, but I was one of those kids who generally had to learn by jacking some stuff up. I was like, if I break this, I'm pretty sure I'll know how it works. I blame my dad, who always isolated us in our room whenever we had guests. So, like, what was I going to do? He left the matches there. He was in the room. Okay, so I totally, absolutely. That was poor parenting right there. Okay, so here's the plan for today. We're going to finish urinary system. We will finish it in plenty of time, in all likelihood, and we will have time probably at the end to do the quiz so that everybody will get 100. Yeah?
Oh, let's do this.
That makes sense? Okay. So the most important thing that I think going into this next test, well, actually, let me make sure that you guys understand what's on the test and all of the stuff that's coming up, and then we'll get into the specifics. First off, Test Wednesday, which includes what topics? Blood, urinary, respiratory. Did you notice that they have a lot in common? They do. Okay, it's not going to be your hardest test because you already had that one, but it's not going to be your easiest test because you already had that one too. So it'll be one of the middle ones, right? And I know you guys are all kind of worn out, but keep trying for a minute. And then let's just talk about the things to come. So Wednesday, you'll take your test. Friday are my last office hours for the semester. 10 to around 2, maybe 3, depending on whether I can get somebody to pick up my kid. It'll be here. I will post the location and everything on melanieb.com to remind you where it is. Your Scantrons from Wednesday will be out there on Friday so that you will be able to look through those. Your grades won't be done yet, like the whole test, but your Scantron will be out. Everybody cool with that? It's the last time you can look over all your tests, all that good stuff, and you can take as many notes as you want. And then your final is the next Wednesday, yes? The next Wednesday at 1:30? Is that right? What time is your final?
Yeah, Wednesday at 3.
1:30 to 3:30? Okay, all right. And then one last thing. On Wednesday after your test, I am going to put up that 10-question assessment quiz. Okay, it's just 10 questions. It is not grading you. It's grading me. And I just want you guys to do your best, but I do want you to do it, and I'm going to give you 2 encouragements or enticements to do it. First, if you do it, I will give you 1 bonus point on the 4th test, just 1, right? And if you do it, I will also post your 4th test score, right? So it's going up Wednesday, like I'll put it up during your test.
On Canvas or your website?
It's going to be on Top Hat. Yeah, yeah, it's going to be on Top Hat. I don't want you to cheat, but I also want you to try, right? So there's no reason to cheat because it doesn't do anything to your grade. Go ahead.
So our test on Wednesday, the grade, when will it be up to know if we have to?
You guys are relatively low priority for getting those graded because your final is on Wednesday, and I've got them Monday and Tuesday. So I would say that probably the latest day would be Sunday or Monday, which is when you guys would get that one done. Okay. In addition, you should be getting your lab scores back. Those take a while to filter to me, but hopefully you will be confident in what you make. As soon as I get them, I will post them on Canvas, but it takes a minute for them to get to me. Go ahead.
Did you say that if you don't want to take the final, you don't have to?
No.
If you're above,
If you have a 92.5.
If you have a 92.5, you can stay home for the final. If you have a 92.4 and you don't show up for the final, I'll enter it as a 0.
It's also after lab. So you have to
What? After lab. Yeah.
So you won't know until like
right.
Well, you might know what you're getting in your lab. I mean, if you've just killed everything, you're fine. Okay? All right. So everybody clear? Okay. I'll put some announcements on melanieb.com and on Canvas. Most of you guys never look at those, so I also try to make sure that they're on the recordings. Okay. So we're going to finish urinary system today. It's totally doable. If you stick with me, you will actually get it. It's not as complicated as it initially seems. The most important thing that you can make sure of going into this test is to make sure that you know how to use these words appropriately. Okay, we will see today that you will do, for instance, sodium filtration and sodium reabsorption, and you're going to end up with an amount of sodium excretion. But you can't use these terms interchangeably. And if I ask you a question about sodium filtration and you answered something about reabsorption, you will get it totally wrong. Okay, so that's why at the beginning of each one, quite often I will ask you questions that seem really obvious, like if we are talking about reabsorption, reabsorption moves stuff from either what structure to what structure or what fluid to what fluid, right? So, and that's in there to reinforce that you know which direction you are moving things and you know how to use these words appropriately, okay? So today, last time we did glomerular filtration, yes? And let's just reiterate. Filtration moves from what fluid to what fluid? Blood to urine. It's called filtrate until it hits the collecting duct, but blood to urine. Everybody cool with that? Okay. All right, sorry. Blood to urine. Now, what if I asked the question differently? What if I said filtration moves from what anatomical structure to what anatomical structure? Glomerulus to the capsule. Bowman's capsule or glomerular capsule, okay? So now we are going to move on, and we did GFR and filtration last time. Now we're going to move on to reabsorption, okay? And so with reabsorption, what we're going to do is, with our metaphor about cleaning the house, what we did is we took everything out and we put it on the lawn. But now what we need to do is we need to select what to bring back in the house, right? And it's going to be selective, which means it's going to use specific transport proteins like carriers or activated channels, and quite often you're pulling things back in either based on concentration gradient, electrochemical gradient, or a specific carrier. Okay, so you guys tell me, reabsorption is going to move substances from what fluid to what fluid?
Urine to blood.
Urine to blood, exactly. Okay, so let's reiterate what we said last time. Your GFR is a boatload, but you reabsorb the vast majority of that. GFR is about 47 gallons per day, or 178, 179 liters. Look at how much of most substances you reabsorb. So you reabsorb about 99.2% of your water, 100% of your glucose. Urea, you don't reabsorb completely because you use it to help regulate your pH, but most substances are reabsorbed pretty dramatically. So we're going to do a boatload of reabsorption, but reabsorption is not willy-nilly like filtration was. You're going to pick things specifically. And so we are going to do reabsorption by a mechanism that we've learned before. So you guys remember way back at the beginning of the semester when we talked about transepithelial transport, right? When we did transepithelial transport, we were moving something from a lumen. This time it's going to be a lumen of a tubule, like the proximal or the distal convoluted tubule usually, yes? And then we're going to move it across the apical surface of a simple cuboidal epithelium cell. Sound vaguely familiar? Apical surface through the intracellular fluid, basal surface, interstitial fluid, through a fenestrated capillary to get it all the way back into the bloodstream. So this is a nice way to end the semester because it basically is going to reinforce stuff that we did at the beginning of the semester. Does that make sense? So what we're going to do is we're going to talk about reabsorption mechanisms for several things. And as we were talking about last time when you guys were leaving, how do you move things across cell membranes? The cheapest, fastest way that you can. So if you can move it passively, you don't move it actively. If you can move it through a channel, you do that and not a carrier, right? If you had to choose between primary and secondary active transport, you would choose secondary. Secondary is cheaper, right? So this is going to be our prediction mechanism that we're going to use, is we'll use the cheapest mechanism that we can to get things across. So what we're going to do is we're going to look at specific substances. I'm not going to teach you the reabsorption mechanism for every substance, but I'm going to teach you the reabsorption mechanism for enough that you can categorize other ones when you run into them as similar to glucose or similar to sodium or similar to other things, right? Okay, so we're going to do the biggies though. We're going to do glucose, right? We're going to do water. We're going to do sodium, and we're going to do potassium, and then we're going to talk about acid, right? H+, what to do with that so you can use that to regulate your pH of your bloodstream. Okay, so glucose reabsorption. So we push glucose out onto the lawn. On a good day, how much glucose do you want to reabsorb? All of it, exactly. But our glucose reabsorption mechanism is going to be limited by the transport proteins that we are going to use. And we've learned about this before. I just want to make sure that it really, really sticks this time. Okay, so when we talk about glucose reabsorption mechanisms, we're going to try to, on a good day, get 100% of it back into the bloodstream because this stuff is like money, right? And how are we going to do it? We want to be not dependent on glucose's concentration gradient, because on a good day, there would be way more glucose over here than over here, right? Okay. So instead, we make it dependent on sodium's electrochemical gradient, right? Which we are constantly working on. Do you see that we're constantly working on this? Okay, so what I do for glucose reabsorption is what kind of transport? Secondary active transport, yes? And this kind of protein, who remembers? What is that? A carrier or a channel? That's a carrier, yes? It just happens to be a carrier that has a seat for glucose and a seat for sodium. But remember, carriers are subject to saturation. If they get full, it limits your transport rate, right? Does that make sense? Okay, so let's just go through it. You guys probably remember it, but glucose gets reabsorbed via secondary active transport by this two-step process. First step is bring it in via a carrier with sodium. It allows us to ignore glucose's concentration gradient because there's such a strong electrochemical gradient for sodium, right? But then, of course, the second step of secondary active transport is take care of the disturbance that you just made by pulling in a bunch of sodium, right? And so this is what? What is that? Sodium potassium pump. Good. Okay, but we didn't get glucose into the bloodstream yet, so let's just finish it and get it all the way into the bloodstream. So now I've got glucose inside, but I don't want to keep it. I want to dump it into the bloodstream, and I do that via what protein? Who remembers? What kind of protein is here? Is this? No, carrier. It has to be carrier because glucose is too big for a channel, right? And then it just diffuses straight in, right? So why does this end up being clinically important? It ends up being clinically important because the transport rate of carrier proteins is subject to saturation. And so if this person right here was a type 1 diabetic who wasn't being treated properly, then let's talk about what happens. So they have boatloads of glucose in their house, right? It all gets pushed out onto the lawn. That is not dependent on saturation, right? Filtration doesn't care about saturation. No, not even relevant to filtration. So you push it out onto the lawn and then you start trying to bring it back in as it goes through the tube, right? But these are limited, right? We only have the number of carriers that we have. And if you can't pull it back in, then let's talk about what happens. If you can't pull it back in, so you pushed it all out here, right? I try to pull the vast majority of it back in the proximal convoluted tubule. That's where most glucose transport goes on. But I don't get all of it, right? Because there was too much that was filtered out. And then it starts going through the tube. And as it goes through the tube, yes, what happens is it exerts an osmotic pressure on the fluid and the interstitial fluid around. And what happens as you get this really non-permeable, high concentration solute going through the tube? What happens to water? Where does it get pulled? It gets pulled into the tube. Yes, gets pulled into the tube. Still gets pulled into the tube. You can even do more osmosis right here, even though it's not surrounded by capillaries. Osmosis doesn't require capillaries. Pulling fluid into the tube, and what happens is you end up with glycosuria, which means you've got really sweet pee, but also polyuria, which means you're peeing like a racehorse, right? Does that make sense? It's the osmotic effect of carrying so much glucose that wasn't reabsorbed through the tube. And that is one of course, the first symptoms of diabetes is that you pee a ton, right? And this is why, right? Does everybody kind of understand that? Because there's going to be another diuretic that's based on that mechanism in just a little bit. Everybody cool? Okay, so glucose, the capacity of your glucose carrier proteins is limited. And if blood glucose is high, then filtrate glucose is high, then delivering glucose through the tube is high. So you get these two symptoms, glycosuria and polyuria. This also happens to you after Halloween, right? Or if you go on a bender because you finished the damn semester and you decide to eat a whole bag of Oreos by yourself because you freaking deserve it. FYI, it's best to do it a bag at a time and not several Oreos every day because you're going to pee out half that sugar. Right? So it's just healthy, honestly. Just kidding. It's not healthy. Okay. No, I'm just saying better one bag all at once than Oreos every day for 2 weeks. That's all I'm saying. Okay. Unless you're diabetic, and then you will croak. Okay. Other things are also reabsorbed by similar mechanisms. Secondary active transport quite often with sodium. Amino acids are reabsorbed by that mechanism. Lactic acid, if necessary, is water-soluble vitamins all have similar reabsorption mechanisms to sodium. They don't all have the same quantity that you're dealing with as sodium. As glucose, but they're all reabsorbed similar to glucose. Okay, so now we're going to talk about sodium ion reabsorption, but you have to pay attention here because we're going to do a two-step reabsorption with sodium. Okay, so what we're going to do with sodium is we are going to move it like most solutes would move. So it's just a solute. We're going to move it across the apical surface, into the interstitial fluid, across the basal surface, into the fenestrated capillaries. Now, most places sodium is actively reabsorbed because if it doesn't favor it moving in, you still need to reabsorb most of your sodium. So what I'm saying is, although you don't always pay for it, you will pay for it if necessary. So quite often ATP is involved in this process. So what we are going to do is we're going to do two-step sodium reabsorption. So sodium got pushed out onto the lawn, okay? It's super duper water soluble and really small and fits through the hole. And we're going to do two-stage sodium reabsorption. The first of it is that right after you put it out onto the lawn, you immediately reabsorb 65% of it. So 65% is immediately reabsorbed at the proximal convoluted tubule by what we call non-regulated reabsorption or obligatory reabsorption. Do you know the word obligatory? Yeah, that's why I stopped using it. Obligatory, like you're obligated to do it, right? Obligatory or non-regulated reabsorption. You have no control over this. It's not influenced by hormones. You can't do a damn thing about it. Just dumped it out on the lawn, pull it all right back in. 65%, okay? PCT has no control over this quantity, but you can control what you do with the 35% that you deliver to the distal convoluted tubule. You with me? Okay, so you pulled 65% of it back in, 35% is still out on the lawn. Now I get to pick what I do with it. And I pick primarily based on some factors. So you guys tell me before we get into it. So just try to predict. I pushed it out onto the lawn. Under what circumstances would I, for instance, want to bring it back in and reabsorb sodium? Can you think of anything that might motivate me to reabsorb sodium? Any idea?
Water retention.
Yeah, what if I had low blood pressure? Then I'd want to reabsorb sodium, right? What if I had low blood volume, even if it wasn't blood pressure? What if I had low sodium concentration in my bloodstream, right? So you can predict that there are some factors that would make you want to reabsorb it. If those factors weren't true, you don't need to do anything because it's already out there on the lawn, right? Does that make sense? Okay, so let's look at how this works, what the factors are that will cause distal convoluted tubule reabsorption. This is called regulated reabsorption, or if you like the old terms, facultative reabsorption. You can control it. It is primarily controlled by two hormones. Do you remember any hormones that are related to sodium? ADH is water. Aldosterone and, coming from the heart? ANP. Yes. So let's talk about those two. Okay, so what is going to happen is, let's talk about ANP first. It's the easy one. Okay, so in response to prolonged atrial wall stretching, that might indicate what about your blood pressure? Okay, yes. So what that will do is ANP will be released from the heart. It is going to target not the proximal convoluted tubule because you can't do a damn thing there. Target the distal convoluted tubule, right? It also inhibits the release of aldosterone, FYI, right? Make sure aldosterone is not released. And what it does is what? Should it increase or decrease reabsorption? Decrease reabsorption. It's going to decrease reabsorption at the distal convoluted tubule. Does that make sense? And also inhibit aldosterone from increasing reabsorption. But then it does one other thing. Okay? So basically what it says is like, it was already out on the lawn. ANP just says, make sure you stay there. And it's like, cool, I stay here. But then it does one other thing, and I want you guys to try to figure this out. This also will help regulate your blood pressure, but this one is not related to reabsorption. It's just consistent with what we did. In addition, ANP will inhibit regulated reabsorption at the DCT, and then it's going to do something to the afferent arteriole. Yeah, it'll dilate the afferent arteriole, which doesn't affect reabsorption, but what does it do to sodium? It increases sodium filtration. Does that make sense? So ANP does both. It inhibits sodium reabsorption, yes, at the distal convoluted tubule, and it increases sodium filtration. Does that make sense? Okay, so go ahead.
Wouldn't that affect the amount of water being reabsorbed too?
Yeah, it does, but water is actually separately controlled. So we'll talk about the water in just a minute, okay? Okay, so the net effect, therefore, of ANP is to decrease blood volume and do what to your blood pressure? Decrease it. Go ahead.
So if you're dilating the afferent arteriole,
Mm-hmm.
wouldn't that cause blood pressure pressure to like localized blood pressure to go down, so less filtration would be happening?
Well, it doesn't actually dramatically decrease blood pressure. This one is just a minor tweak to increase flow, to increase GFR. If you really massively dilated it, you would actually drop the pressure. But if you just open it up a little bit, it's just like a big tube versus a small tube going into that filtration membrane. Go ahead.
Is that like auto-regulation instead of systemic? It's like the localized.
Well, this is hormonal, so it has to be systemic, right? But it's minor.
But like when you dilate the vessels. Like
Yeah, you dilate the vessels. It's just a minor change in the local area. You're not dilating them enough to drop the pressure. You're dilating them a little bit so that you can actually increase flow, right? So you're in the sweet spot, basically. You're opening it up a little bit to increase flow, but not opening it up so much that you decrease pressure dramatically. So, yeah. So you can actually just do bigger tube without dramatic change in pressure, but you're just increasing flow. And since the efferent arteriole is still constricted, it's actually going to make sure that the pressure in the glomerulus is still high enough for filtration, because you didn't open up both of them. That would definitely drop the pressure in the filtration. You only opened up the afferent. Go ahead.
It was just me thinking with pericarditis dilating a regional vessel, it makes one side of the vessel larger than after the vessel. So you got point A and point B. It's point A bigger than point A. Is that what it would do?
Yes.
When it dilates,
It's changing a P1 and not the P2. It's changing one location and not the other. So the message here, and it's a good question that Toby asked, is that can you increase flow without dropping pressure dramatically? And if you do it with it just minorly, you can increase flow. It's not a massive increase in filtration, by the way. It's just a little increase in filtration. Okay, so let's talk about the other situation. Are there any situations in which you would want to reabsorb that 35%? Yes, there are situations in which you would want to reabsorb that 35%. Here are some reasons you might use. First, look at the house, right? So look at the blood. Do you have a low blood volume? Even if your blood volume is fine, your cardiac output might not be big enough to maintain your pressure, or your blood pressure might be low, or your blood flow might be low. Any of these, even though these aren't kidney problems, the kidney says, hey, you got a flow problem, I got one solution. If this is a nail to the kidney, everything, if he's got a hammer, everything looks like a nail at the kidney. So he's going to say, you got any flow problem, this is what I can do for you. And I will increase reabsorption and therefore fluid, because pump fluid tubes, right? I will increase reabsorption at the distal convoluted tubule. So these are three of the triggers. They're not the only three. In addition, although we don't usually talk about it, you can also look at the P. What if the P had too much sodium in it? Then you could say, okay, I'm going to use that as my trigger for reabsorption. So mostly you look at the blood, but sometimes you look at the P. Okay, so here's how this goes. You already know this. We just have to put a couple little details in. So you already know that the juxtaglomerular apparatus is going to monitor multiple stimuli, among them the pressure in the afferent arteriole. You guys remember this? Okay. So it's monitoring the pressure in the afferent arteriole. We won't talk about it a lot, but it's also monitoring what's going on in the distal convoluted tubule. Okay, so let's talk about this part of the story to put it all together. This is the same story we've been telling with just a little bit more detail. If you detect low pressure in the afferent arteriole, then the juxtaglomerular apparatus will secrete a hormone enzyme thing, renin, right? It's going to end up making a hormone. And renin will convert angiotensinogen to angiotensin 1. Sound familiar? And then if ACE is around, you get angiotensin 1 converted to angiotensin 2. And then we know what angiotensin 2 does to the vessels, but we're interested in the impact on the kidney because angiotensin 2 will cause the release of aldosterone. Yes? Sound familiar? And remember what aldosterone does. Let's remind ourselves. Okay? Aldosterone, now all we're going to do is add just a little bit of detail. We've known for a while that what aldosterone does is it causes sodium reabsorption, okay? But now let's tell you where. Primarily at the distal convoluted tubule, because you can't control the proximal. Yes, proximal does what it does. And so what it's going to do is aldosterone, okay? aldosterone will target the DCT and it will cause sodium reabsorption and potassium and H+. There's different transport proteins for what. So one of them moves sodium and potassium. The other one moves. Okay, you guys with me? So this is just adding some renal physiology to it. So we've known for a while that aldosterone causes sodium reabsorption and potassium secretion. Now the details that you're going to add is that aldosterone causes regulated sodium reabsorption and potassium secretion at the distal convoluted tubule. And it can go up to how much sodium reabsorption secretion? Sodium reabsorption? 35%. From 0 to 35%. That make sense? So what is happening is all that 35% is out on the lawn, and then I can decide how much of it to bring back in based on how much aldosterone is present. Is that good? Okay. And aldosterone would be present under conditions in which the kidneys might have detected low blood pressure, low blood volume, something like that. Does that make sense? Okay. All right. So the juxtaglomerular apparatus monitors these stimuli, primarily the blood, but we didn't talk about it. It does monitor the filtrate too, but that one's kind of complicated. And aldosterone causes increased regulated DCT reabsorption of sodium in the distal convoluted tubule. The net effect is an increase in sodium ions and water. We'll see water in just a minute. We haven't talked about it yet. And this results in an increase in blood volume and therefore a what in blood pressure? Increase in blood pressure. Okay, so we already know that angiotensin II also raises blood pressure by causing systemic vasoconstriction, but that's not specific to kidneys. Okay, the opposite, by the way, guys, is also true. How do you inhibit the release of aldosterone? Have those other things be true. If you detect high blood pressure or high blood flow to the kidney or high osmolarity of the filtrate, this decreases renin, decreases angiotensin, decreases aldosterone, and increased sodium is lost in the P, okay? So remember, of course, though, that whenever you do this, it costs you something, yes? When you reabsorb sodium at the proximal convoluted tubule, it doesn't cost you potassium or H+. When you reabsorb it at the distal convoluted tubule, it's always going to cost you something. So keep that in mind for when we start talking about diuretics. Do you know that some diuretics cause massive losses of potassium? Okay, we will learn what that is and what's going on in just a minute. Okay, so now potassium reabsorption. Ready? Not potassium secretion, that's different. Okay, so we just dumped potassium out onto the lawn. How much do we bring back in? At the PCT, you always reabsorb 90% and leave 10% out on the lawn. We always lose potassium as we go through the kidneys. Okay? So 10% minimum is lost, but stick with me, guys. Under the presence of aldosterone, won't we lose more than 10%? Yes? Because once you get to the kidneys, or once you get to the distal convoluted tubule, if aldosterone is present, you're going to go down from 10%, right? Because you're going to secrete more out. So, of course, you've been a human for a while. Are you more likely to be deficient in potassium or sodium? Potassium, yeah. We don't put it on every damn thing that we eat, and we also lose 10% minimum, right, as we're going through the kidneys. Does that make sense? There's no reabsorption mechanism for that last 10%. We don't have any more reabsorption transport proteins. So you always lose potassium, and that's why we can go back to this picture right here, or this table. Just briefly look at potassium. Generally speaking, how much potassium do we get to keep? Only about 86%. Potassium on a good day. Okay, so keep that in mind, and then we'll talk about diuretics in just a second. What about negative ions? Well, luckily, we work so hard on actively transporting our positive ions that we don't have to worry about our negative ions because there are channels for them. And if you create a massive electrochemical gradient because you're working so hard on sodium and potassium, then you basically get chloride and bicarbonate for free on most parts of the tube. Does that make sense? You just create a huge electrochemical gradient of positive ions that you're moving in, and then the negative ions are like, hey, wait for me. And then they just come straight along. So you don't have to worry about them. Okay? All right, now let's talk about water reabsorption. Now, water does follow sodium when it can, but it can't always. So basically, remember way back when we talked about osmosis, we said that solutes suck, right? And sodium sucks the most. So what's happening is I move massive quantities of solutes, both positives and negatives, from the lumen to the intracellular fluid, to the interstitial fluid, to the blood plasma, is that I am increasing solute concentration and therefore decreasing water concentration, right? Okay, and I'm creating an osmotic gradient for water to move in, right? So as long as you are moving solutes, then water will move in wherever it can via what transport mechanism? Osmosis. Okay, there are some places where osmosis is less possible, so let's talk about that. So water is basically passively going to move through to follow these solutes. And then don't be surprised that if you move 65% of the sodium at the PCT, then you reabsorb 65% of the water, and you don't have any control over that either. So basically, you push sodium out onto the lawn. As the sodium moves back in the house, the water goes with it in the proximal convoluted tubule. You can control what you're going to do with that last 35%. So non-regulated reabsorption of water happens at the PCT, and it's 65%. Regulated reabsorption of the water happens at the DCT and the collecting duct. And then we'll talk about one other water reabsorption place that isn't in your notes, but I want to tell you about it. Okay, so at the DCT, what is going to happen is in order for water to follow sodium, you have to account for the fact that the cells are different in the PCT and the DCT. Look right here. Here's the proximal convoluted tubule. We have leaky tight junctions. Osmosis not only happens very readily through the cells because of boatloads of aquaporins, but also between the cells because of these leaky tight junctions. Well, these little buggers are not leaky at all. It's the distal convoluted tubule. And the aquaporins are controllable, which is part of how we discovered that it wasn't just like sneaking through. There was something that was controllable, like otherwise water would just follow straight through. So this is relatively impermeable to water unless ADH is present. Okay, that's the distal convoluted tubule. So let's look at what happens at the distal convoluted tubule. At the distal convoluted tubule, you can reabsorb up to 35% of the water, but the cells must contain ADH. So ADH targets now the distal convoluted tubule. Where does ADH come from, guys? You can do it. Last class had no idea either. So posterior pituitary. You're like, I have stopped thinking about that. Shut up. Posterior pituitary. Okay, so here's how this works, guys. If let's talk about when ADH would be low. Okay, so remember, you've learned this story before. When would my ADH be low?
When would your ADH be low?
Under what circumstances would a person's ADH be low?
You have a lot of water.
Yes. Okay, I'm drinking a lot of water. Trying to change one of my bad habits, which is not drinking enough water. So trying to drink 2 of these bastards per day. It feels like a second job, honestly. I'm like, oh my God, this is awful. Okay?
That's
No, that's actually like what people are supposed to drink. They're supposed to drink 1.5 of these per day. It's like 64 ounces. I hate, it's just like the worst. But anyway, so what happens is if I drink lots and lots of water, then the blood that is being delivered to my hypothalamus and my posterior pituitary is going to be relatively dilute, right? Not concentrated in solutes. What that will do is inhibit the release of ADH, right? If ADH is not present, what happens to that water that I put out on the lawn? It stays there. Yeah, you don't reabsorb it, yes? Okay, so if ADH is low, water can't pass through the DCT cell membranes. Those aquaporins are apparently controllable. They still don't know quite how it works, even if the sodium ion reabsorption is occurring. So what this does is in the absence of ADH, I don't care, you can reabsorb sodium if you want to, but water's not going with it. Are there any circumstances in which you need to reabsorb sodium but not water? Yeah, hyponatremia, right? What if the primary issue that I was dealing with was sodium loss and not water loss, right? So you can actually discouple them, right? So you can reabsorb sodium without reabsorbing water. Okay, and then of course in that situation, if you're secreting a whole bunch of ADH, then you are going to peel it. Yes? Okay? Got it? So large quantities of dilute urine will be excreted. That's polyuria. Remember, we did learn a disorder that caused polyuria specifically because of low ADH, and that was diabetes insipidus, right? Good? Okay. Now, under what circumstances would your ADH be high? would you be releasing a whole bunch of ADH? What? If you're dehydrated. So what I would like to do instead of drinking water all day, and I can't do, I'm in my 40s, I would like to drink coffee until it's time to drink wine. And then, yeah, that's what I prefer. But apparently it's not really good for your system. And in your 40s, it's going to be like the worst thing ever. So this instead is happening. There's no coffee or wine in here. What? Okay, so if ADH is high because you are dehydrated, then what's going to happen is, of course, you are going to be delivering to your brain relatively concentrated blood plasma, right? And when that actually is encountered in your hypothalamus and posterior pituitary, you are going to release ADH, which is going to target where in the nephron again? Distal convoluted tubule of the nephron. And that is going to allow water to follow sodium. Yes? It's going to open up your tight junctions, let the aquaporins work their freaking magic that nobody quite understands yet. We didn't even know they had them when I was in school. They're like, what the hell is an aquaporin? So, so what's going to happen is water is going to be reabsorbed. ADH will also cause the thirst response, and you're not going to pee very much, right? So if you're dehydrated, you're going to release ADH, and you're going to pee small quantities of really, really concentrated urine. You know, where like it's so concentrated that it's like stinks up the whole bathroom, and it's almost like paste when it's coming out. You're like, oh, I definitely need to drink some water. Okay. ADH released, we already talked about this, but it's primarily controlled by the osmolarity of the blood that is encountered at the brain, right? ADH, however, can also be released if your brain encounters low blood volume or low blood pressure. It's not the primary mechanism, but it's one of them. Okay, what about lipid-soluble stuff?
Does what it wants.
Yeah, it does whatever the hell it wants. So if like lipid-soluble stuff in my stupid metaphor that I keep using, lipid-soluble stuff gets pushed out, but it's a ghost and it just goes straight back through the walls into the house, and you push it out again, it goes straight back in. So you have no control whatsoever over what lipid-soluble stuff does. It's going to go straight out, straight back in, down its own concentration gradient. They are reabsorbed easily. There's no regulation. You can't really get rid of fatty, soluble stuff through your kidneys. Drugs, toxins. This is important for those of you guys who like marijuana. Marijuana is lipid soluble, guys. Your kidneys are not going to do a damn thing for you about marijuana, whether it's legal, illegal, whether you're in California, Colorado, or you're going to get a pee test tomorrow. Your kidneys are not going to hook you up with a lipid soluble drug like that. It's just going to get pushed out and pulled right back in down its concentration gradient because it's lipid soluble. Okay, so lipid soluble anything is hard to clear out of the body. In addition, if you are chubby, marijuana stores in your fat cells, which is an amazing evolutionary thing to think about, right? Because marijuana is actually a lipid-soluble thing that you grow and then smoke and then stores in your fat cells and makes you want more marijuana, right? So it's like a little evolutionary, it's like it's controlling you. It's like making you farm it, right? It's like keep making more of me. It's really clever if you think about it. Okay, so what about stuff that got put out onto the lawn and didn't have a reabsorption mechanism? Then it ends up staying there. That's why filtration is actually relatively useful, because anything that gets pushed out onto the lawn and is too big to reabsorb or doesn't have a reabsorption mechanism just by default stays out there. So, or it can get reabsorbed incompletely. Urea and uric acid are reabsorbed incompletely, usually primarily to manipulate blood pH. Creatinine, you dump it and you don't reabsorb it. So basically, if you put it out there and there's no reabsorption mechanism, then it ends up in the toilet. Okay, but we have to do one thing that isn't in your notes, but I do want to tell you about, which is kind of cool. There's one other way that you work on water reabsorption. It's not hormonally dependent. It happens not in the PCT or the DCT, but the loop of Henle. You ready? So I told you guys before that the loop of Henle was primarily about water reabsorption, but there's this kind of special cool way that it does water reabsorption, okay? So we did 65% of the water reabsorption here. We do water reabsorption here too, but this has this magical little way that the longer it is, the more water conservation we get. So it's actually involved in the 35%, by the way. They just kind of lump those two together. But this one is kind of regulated differently. It's primarily regulated by manipulating the osmolarity of the medulla. So you guys remember cortex and medulla, right? Okay? All of this stuff that we've been talking about primarily goes on in the cortex, proximal and distal convoluted tubule. Now I'm going to talk about what happens in the medulla. You ready? Okay. So it's going to seem confusing at first, but it's okay. It'll be fine. Okay, you ready? Talk.
The countercurrent multiplier, also known as the countercurrent exchange system, is the method that the nephron uses to concentrate urine. For a lot of people, just the name of this process is daunting. Countercurrent multiplier sounds like a complicated math formula or something, but it's really much easier than it sounds. To begin with, let's look at the anatomy of the nephron and its place in the kidney. If you recall, the kidney is divided into the outer portion, the cortex, and the inner portion, the medulla. The glomerulus and proximal tubule are located in the outer cortex. The loop of Henle descends down into the medulla of the kidney, loops around, and comes back up. By the time it becomes the distal tubule, it's back in the cortex. The collecting ducts then descend back down into the medulla and eventually empty the filtrate into the calyces and renal pelvis. For starters, I want you to think of the medulla as being very salty. In fact, at the bottom of the loop of Henle, the sodium concentration is about 300 milliequivalents per liter, which is double that of the blood. The loop of Henle has some special characteristics that explain why that is, and it's really all about saving energy. So the descending loop of Henle is extremely permeable to water, but it's impermeable to ions. So water is able to passively diffuse out of the descending limb, where it is reabsorbed by the vasa recta, the vessels that surround the loop of Henle.
Okay, so keep this in mind. We're going to do two things. We're going to run the descending by the ascending, right? Okay, and they're going to run counter to one another. Do you guys remember from physics that if you get things running opposite directions, you get really good exchange between them? So this will be called the countercurrent multiplier. This one is going to be super, super permeable to water, and so water will diffuse out and therefore into the capillaries really readily. But this one is going to really, really actively transport ions. So watch.
The ascending limb, especially the thick segment, however, is the opposite. It's impermeable to water, but will use energy to actively pump ions like sodium and chloride out of the tubule into the interstitium of the medulla. When it does this, it creates a hypertonic environment around it. Because the descending limb is very permeable to water, water leaves the descending tubule without expending any energy because it is following the concentration gradient.
Okay, so these two are running by one another, and do you remember that there's capillaries around here? Right, the vasa recta capillaries. So what the ascending limb is going to do is actively transport ions into the extracellular fluid or the interstitial fluid, right? And so this is going to be super duper salty, and then it's going to be right next to its friend, which is really permeable to water. So where's water going to move? Out of the tube, right? And ultimately it's going to get reabsorbed into the vasa recta there. Does that make sense? So, and since these run by one another, and one of them is really actively making it salty, and the other one is actually passively diffusing water or osmosising water out, the longer the loop of Henle is, the more water reabsorption you get. So this goes back to the thing that I told you guys before. In desert animals, the loop of Henle is incredibly long because we want as much water reabsorption as we can possibly get before we actually dump it into the collecting duct. Does that make sense? So this is this little way that's not really dependent on anything else that's going on with proximal and the distal convoluted tubule to actually reabsorb water, but just in the medulla. Okay, almost done.
Do all those ions also,
So it is called count.
What?
do all those ions also get absorbed into the vasa recta?
No, you can control which ones you absorb into the vasa recta. So they're just getting put into the interstitial fluid, and you can either dump them or pull them into the vasa recta depending on the transport proteins. But the vasa recta is primarily just doing water reabsorption. So a lot of those actually just get dumped into the extracellular fluid and then diffused. A lot of them will eventually get picked back up, but not right there. Okay?
Current because the filtrate flows in opposite directions, down the descending loop and back up the ascending loop. It is called a multiplier because the active pumping of ions out of the ascending tubule multiplies the amount of water that is reabsorbed from the descending tubule. As more water is pumped out, the filtrate becomes more and more concentrated.
He said water's pumped out, but water's not pumped out. Water diffuses out. The ions were pumped out. So basically what we have is two loops. One of them is actively working on ions. The other one is passively moving water out of the tube, ultimately making it back into the bloodstream. Does that make sense? Go ahead.
So the ascending loop is the one that pumps out the ions, right?
Yes, the ascending moves the ions and the descending is permeable to the water. And it doesn't really matter, even though you go descending then ascending, but they're right next to one another, right? So collectively, this is why like together they work, right? Together. That makes sense? Okay, so yes, it's following. Go ahead.
So the countercurrent is all talking about the loop. It's not, you're not really factoring in the vasorecta around it.
Some people say that the vasorecta is part of the countercurrent multiplier, but the vasorecta doesn't run counter, right? So that's how I learned it. But the first time I learned it, I was like, oh, well, it's called countercurrent because the blood and the filtrate are running opposite to one another, but they're actually not running opposite to one another. When I was reading, and I decided to read up on it again last night because I don't usually teach this, but I decided to teach it this time. When I was reading last night, the best explanations were that the ascending and the descending loops are counter to one another. And that's why it's a countercurrent multiplier, not what's going on with the bloodstream. Does that make sense? Okay. And that is what makes sense to me, even though I was taught it differently when I was taught it as an undergrad. Okay. So what do I want you to know about this? Couple of things. Since it's not in your notes, I'm not going to hold you responsible for a lot of detail about it, but let me ask you 3 questions to make sure that you get the big picture. Okay. First off, what are we controlling reabsorption of here? Water. Yes. Got it? Okay. And we are controlling reabsorption of water in what anatomical structure? Loop of Henle, which is part of where? The cortex and the medulla. Medulla, exactly, right? All of the other reabsorption that we talked about was cortical reabsorption, and this is medullary reabsorption. Medullary reabsorption of water. Okay, got it? Okay, go ahead.
What do you have coming out of the ascending?
That's just an X plus, it's just an ion. Just any ions. It moves a bunch of them. Mostly sodium and chloride, though. Okay? Everybody good? All right. So, the third phase and the last phase is just secretion. And secretion is actually simpler. There are fewer things that you have to keep track of with secretion. The primary one that you're going to have to keep track of are those 2 guys over there, potassium and H+. And secretion, again, remind us, when you were doing secretion, you were moving stuff from what fluid to what fluid?
Blood to urine.
From blood to urine, but this time it's going to be selective movement, right? It's like the last time that you go through the house, you open up all the cupboards, right? You make sure you get rid of any waste product that you didn't catch before, and any excesses that you have. The primary effect of secretion is to get rid of any nitrogenous waste that you didn't catch, ammonia, urea, uric acid. Also, there are certain things that we actually have secretion mechanisms for, like penicillin and phenobarbital. And then remember that this is secretion, right? Secretion of H+, and potassium. So let's just talk about potassium. If you ever had excess potassium, aldosterone will make it get exchanged for sodium, and this would cause potassium secretion. Where's aldosterone from again? Adrenal cortex, exactly. Okay, so I don't want to complicate things, but I told you a bunch of reasons that aldosterone might be secreted, right? Low blood pressure, or low blood volume, or low sodium concentration in the bloodstream, or high in filtrate. Just to throw it out there, you can also secrete aldosterone because of potassium concentration, right? So, for instance, it would be a high potassium, like hyperkalemia, would actually cause that to be secreted, which doesn't happen very frequently, so it doesn't end up being really relevant to most stories that you have. But you can control potassium secretion with aldosterone levels. And then we'll talk about H+ in just a second. Okay, so aldosterone can also manipulate this H+, but let's talk about just H+ in general and what the kidneys can do to help with your pH. The kidneys are pretty powerful for helping you with pH because they can do that same thing that happened in systemic capillary red blood cells. So here, watch what the kidney does. So the kidney, inside your tubule cells, mostly in the distal convoluted tubule, what's going to happen is you will, again, force this equation this direction. But you're going to be really, really powerful at changing blood pH if you figure out what you want to do with each one of those. Does that make sense to you? So, for instance, inside the epithelial tubule cells, you will force this equation, and then if your blood pH was too acidic, what do you think you would do with the H+?
If it was too acidic?
Yeah, you dump it. What do you think you'd do with the bicarbonate ion? You'd reabsorb it, exactly. And so you can really dramatically manipulate your blood pH. However, if your blood was too basic, what would you do with the H+? You pull it back into the bloodstream. So the kidneys can really dramatically change your blood pH. The two most powerful systems for regulating blood pH are the respiratory system and the urinary system. Okay, does that make sense? So you can do whatever needs to be done with that H+ and also with the bicarbonate ion. So was the low blood pH due to anything related to the kidney or anything related to carbon dioxide? It doesn't have to be. The kidney is a one-trick pony with helping with pH. It'll decide where to put those two things, regardless of whether they came from lactic acid buildup, whether they came from carbon dioxide, whether they came from drinking too many sodas. It doesn't make any difference. This is what the kidney will do to help you with it. It'll say, if you're too acidic, I'm going to get rid of H+, and I'm going to do it by this mechanism. Okay? I can control it really dramatically by this mechanism. If you're too basic, I'll hold on to H+. So whatever was the reason for your low blood pH, this is how the kidneys will help with it. Good? So you guys have probably seen that a lot of people are doing things like trying to manipulate their pH of their bloodstream by like drinking alkaline water. Have you guys seen this? It's a total waste of money. Okay? And it's kind of dumb because I don't think we needed to improve on water. Do you guys? Okay? Especially if we had to pay $3.50 for it instead of, you know, getting it out of the tap or filtering it a little bit, right? In addition, it basically is just making your kidneys work slightly harder than they otherwise would have. And it's completely unnecessary for most of us. You don't need to drink alkaline water, and you don't need to do a detox with that alkaline water unless your kidneys and your respiratory system are failing you. And then you will have pH problems that will not be fixed by alkaline water. Okay. So, to summarize, let's summarize. Okay, what happens in the proximal convoluted tubule? Well, none of it's regulated. So whatever happens in the proximal convoluted tubule happens in the proximal convoluted tubule, right? And primarily you are going to reabsorb 100% of your glucose if you can. How much of your sodium? 65% of your sodium. How much of your potassium? 90% of your potassium, and then your negative ions will follow the positive ions mostly, right? And you can't control any of that, okay? What was your question?
Just about percentages.
Okay, you will, and I'll show you where to practice that in just a second. But in the distal convoluted tubule, right, you can control some things, yes? Some things you can't control, like for instance, the negative ions will still follow the positives when they move, but if you can control the movement of the positives in the water. So in the distal convoluted tubule, my question is, what will happen if aldosterone and ADH are present? What things will move and what direction? You ready? Okay. In the distal convoluted tubule, if ADH and aldosterone are present, sodium will be reabsorbed, yes? Yeah? But the movement of the positively charged ions has to be canceled either by moving negatives or by swapping with other positives. So water will follow sodium, but only if what hormone is present? ADH. And chloride and bicarbonate will follow sodium if they can, right? And whatever you didn't follow with a negative will get swapped with a positive, right? You'll do H+ or K+ out. So the summary of the summary is this. In the DCT, if aldosterone and ADH are present, you will reabsorb sodium, chloride, bicarbonate, and water, yes? And you will secrete potassium and H+. Does that make sense? Okay. Everybody good? All right. So that's all the hard part. The rest of this is easy. Okay, let me show you something though. I'm going to post this for you guys today. You can do it if you want to. I'm not going to grade it, but it's just a place to practice. So I made this for you. Okay, so this is just a couple of things that you can do to practice urinary system. But in addition, this is reabsorption and secretion. So what I've asked you to do is I drew a really bad picture of the PCT and then a really bad picture of the DCT, right? So this is PCT. If it were me, I would color this P color and that blood color, so I keep it straight, okay? And then I ask you specifically the substances, glucose, sodium, potassium, water, chloride, H+, and bicarbonate, okay? I want you to tell me where they're moved, what percentages, and then if there is a hormone that is responsible, where is it going to be responsible? So for instance, if we're at the DCT, right? Sorry, wait. If we're at the PCT, any hormones relevant to PCT?
No.
No. If we're at the DCT and we're moving water, what's the relevant hormone? ADH, right? And you will do percentages, and you will do hormones, and you will just reinforce. You don't have to do this if you don't want to. It's just a lot of people need a way to practice, like figuring out which things. And you don't just reabsorb, you also secrete. So figure out what's moving which direction. So this is just a little place for you guys to practice a little bit about the urinary system. Okay, so last thing that we are going to do is final volume of urine, and we'll talk about kidney stones, and then we'll take 10 minutes and do your quiz. Okay, so everybody should get 100 on your quiz, right? All right, so we tend to make around 1 liter to almost 2 liters of urine per day. But my question that I'm answering here is what determines the final volume of urine that you make, okay? So there are some obvious things, you know, like how much you drink. There's some less obvious things like temperature, like blood pressure, those kinds of things. And then we'll talk about diuretics and how diuretics work. You ready? Okay. What's your predictor about blood pressure? If you have untreated hypertension, what do you predict about your GFR? It's going to be high, and therefore your urine is going to be high, right? You're going to try to reabsorb a whole bunch of it, but you're always going to lose a little bit of fluid more than you otherwise would. So GFR varies with blood pressure, increased filtration. Note to self that reabsorption is expensive and filtration is not. And so it's a little hard on your kidneys to have chronic hypertension and also the reabsorption that's necessary because of your chronic hypertension. Okay. In addition, the pressure itself is hard on your glomeruli. Okay. Now, the blood concentration. Now, I know you went all the way to the end of physiology so that I could teach you that if you drink a lot, you pee a lot. And if you don't drink very much, you don't pee very much. But now what I want to do is I want to make sure that you understand the little physiological tweaks in between that. You ready? So this is the relationship. Make sure that you understand it. If you drink a lot of water, not pathological amounts, but 2 of these bastards per day, which feels like a second job, honestly. So if you drink a lot of water, then the water concentration of your blood increases, and the relative solute concentration decreases. Your hypothalamus and posterior pituitary will say, okay, inhibit ADH secretion, yes. And ADH is therefore not going to allow for water reabsorption. Where? Distal convoluted tubule, primarily, yes. Even if sodium ion reabsorption was happening, water ion reabsorption would not, or water reabsorption would not. So if you drink a lot, you inhibit ADH secretion and stop regulated reabsorption at the distal convoluted tubule, and therefore you pee a lot. Yes? Got it? And if you're dehydrated, the whole story goes like this. If you're dehydrated, you deliver relatively high solute concentration blood plasma to the hypothalamus and posterior pituitary. ADH is therefore secreted. ADH targets where again? Distal convoluted tubule, and allows for regulated water reabsorption at the distal convoluted tubule. So if you don't drink much, you don't pee very much. But because of ADH secretion targeting the distal convoluted tubule, right? Okay. All right. So now that one you got. You should be able to tell that story. Temperature you may or may not have. Okay. So when you're exposed to high temperatures, you do not tend to pee very much. You might not notice that you don't pee very much. So when you're exposed to high temperatures, exactly, when you're exposed to high temperatures, it causes cutaneous vessels to dilate and it activates sweat. And you lose both water and sodium in sweat. And as the fluid in your body decreases, it came from your blood plasma ultimately. Then ADH and aldosterone will be secreted, right? And those will cause what? Sodium and water reabsorption at the distal convoluted tubule, right? So if you're really hot, you sweat a lot, which causes you to ultimately, not directly, release ADH and aldosterone, right? Which causes regulated reabsorption at the distal convoluted tubule, and then you don't pee a lot, yes? So if you sweat a lot, you don't pee a lot. Yes? Got it? Okay, but this is the one that I find interesting. I'm not the only person who camps in here, right? You guys camp? Okay. All right, no? She's like, hell no, I don't camp. Mariah's not here. I always like to ask her if she camps because she totally looks like someone who would camp, doesn't she? No. So, I don't think so. So, but why is she not here today? She's always here. Okay, so if you are exposed to low temperatures, and like for instance, camping, you know what's going to happen if you camp and it's like 25 degrees in the middle of the night, right? And you're in the tent with everyone in your family, right? There's a dog, 3 children. You're going to have to pee. You know it's going to happen. Happens every damn time, and it's the only time that I actually really, really do have penis envy. Because you know you're going to pee on your shoes if you're a woman. You're like, it's going to happen. They're really big and easy to find.
That's jacked up.
Okay, so why do you have to pee when you're camping? It's because when you are cold, your cutaneous and peripheral vessels will constrict, and you still got the same volume of blood. So what does it do to your blood pressure in your abdominal pelvic cavity? It bumps it up, which does what to your GFR? It increases your filtration, and therefore you have to pee a lot. So you pee more when you're cold, and it's terrible, right? It's especially for women, right? It's awful. It just seems what?
We have devices for that.
I know, but then you have to find a pee-covered device in the middle of the night and your shoes. Like it literally never seems like worth it.
You put them together right before you fall asleep.
Well, the point is you would
That's a
leave
lot.
with 10 bucks.
That's a lot.
Oh, you wouldn't have to leave the, oh my God, my children would. No, I can't make it into a bottle. It's just not going to happen. I don't have that skill.
You could.
Okay. Yeah, I know. I've got a friend who carries one of those around, and I'm like, that means you were always carrying something around that had pee on it.
No, no. Carry your
I mean, this
bag.
is if it
No,
was
it's-
camping, you wouldn't be sure. Blue game.
Okay. Okay.
That's why you just buy normal.
Yeah, and well, we solved the problem by buying an RV. No, we don't. Yeah. So no, it's not really camping anymore.
Whatever camping.
Not with an RV.
With 3 children and a dog, I earned that damn RV. You guys be quiet. It's got solar panels on top, so I don't feel guilty. It's got a door. Children. Okay. Diuretics. Let's talk about how diuretics work. You ready? Okay. So diuretics are generally given usually for what kinds of disorders? Usually hypertension, right? They can be given for a lot of different things, but what diuretics do is, of course, increase the production of urine, right? And usually it has the impact of dropping your blood pressure, and it's quite often while they're given. But there are a bunch of different ways that you can manipulate that. You can work on the PCT, you can work on the DCT. I don't know any that work on the loop. Or you can deliver an osmotic diuretic like glucose is in diabetics, right? Something that gets pushed out but just pulls fluid through the tube as it goes through. So let's talk about the categories of diuretics, and we'll talk about alcohol and caffeine too. Okay, so the most powerful diuretics are also the most dangerous, but you have to listen to the reason that these are the most dangerous. These are the ones that work on the PCT reabsorption, and I know I call it non-regulated, but we do have drugs that can regulate the reabsorption there. We have drugs that it can impede PCT reabsorption of that 65%, okay? Now, what's going to happen in that situation, though, is important for you guys to understand, because if you don't reabsorb it here, yes, in the PCT, you're definitely going to try to reabsorb sodium here, okay? And when you try to reabsorb it at the DCT, it always costs you something. Does that make sense? So if you deliver a diuretic that impedes PCT reabsorption, you're going to do boatloads of DCT reabsorption. And when you do that, you can have a dangerous loss of potassium and or a disturbance of H+. The potassium is usually the one that gets you really, really quick because it can, of course, cause hypokalemia really quickly and cardiac arrhythmias. So these are the most powerful diuretics that we have, but quite often when they are given, like Lasix, like hydrochlorothiazide, they're given with a drip of what? Potassium, yes, exactly, right? They're super powerful. Now, I know it's confusing, but they don't actually affect that part. They just deliver too much sodium to that part, and therefore this part continues to go. Does that make sense? So these are not usually medications that you would be given as maintenance medications, but inpatient medications far more frequently, okay? Now, the ones that are not as powerful work on the 35%. But these are potassium-sparing diuretics because what they do is they inhibit this. And then you just leave that 35% of the sodium out on the lawn, right? Does that make sense? So you just leave this out, they inhibit that. But they're potassium-sparing. They don't cost you any extra potassium. As a matter of fact, if they do anything, they preserve some of your potassium, right? Okay, but they're not as powerful. Spironolactone is one of those, and they are given as maintenance medications. You can have them take home and take the diuretics. Okay. So there's two different categories. And then there are the other things. Let me talk about the osmotic diuretics, and then I'll do alcohol and caffeine. So osmotic diuretics are a diuretic that delivers something that you usually take them orally, and then they are going to have something that we know will get filtered out and has no reabsorption mechanism, and it's going to exert osmotic pressure as it goes through the tube, right? These are osmotic diuretics. Mannitol is one of them. The reason that some of you guys may have encountered them is because they're sometimes sold in over-the-counter medications for premenstrual bloating, a lot of times like Premsin. So there are drugs that you can take when you're having premenstrual bloating and you're like super retaining water because of hormones. And what these will do is they will just deliver an osmotic diuretic that goes to your kidneys, gets filtered out, and can't get reabsorbed. Are they dangerous? Not if you use them as directed, but some people with bulimia and anorexia will use them really, really regularly to get rid of excess water weight. And they become really dangerous if you start doing that because, of course, they can lead to all of the hypo disorders. If you're losing boatloads of fluid, you can lose too much sodium, too much calcium, too much potassium, right? So they're not dangerous when used as directed, but they have been responsible for deaths. But you've got a woman who, instead of using it for 3 days during her cycle, is using it every day at double and triple the dose. And they can kill you, right? They can cause massive osmotic disturbances. Okay, and then the other two that are anecdotal diuretics, like you don't take them because they're diuretics, but they have that effect, is caffeine. Caffeine is a diuretic because it increases your blood pressure. And so it increases your GFR. That makes sense? Okay. If you want to get a really, really good effect, you drink an Irish coffee because that's coffee and alcohol simultaneously. And what alcohol does is alcohol inhibits the secretion of ADH. And therefore you can lose that 35%. Does that make sense? Okay. So that's how all of those work. Okay. Last little tidbit and then we'll do your quiz. Kidney stones, just briefly. The hell is a kidney stone? You ready? Okay. These little bastards. Okay. So you're getting rid of a whole bunch of minerals. Calcium and magnesium really, really like to crystallize when they're in high concentration. So you're getting rid of a bunch of minerals. And if they sit in high concentration in your minor calyces, major calyx, or renal pelvis, then often crystals will start to form. And these little bastards have to be passed through your ureters, then they're going to dump into your urinary bladder and you're going to feel like you're fine. You're not fine because then they have to pass through your urethra. And this is where I'm really happy that I don't have a penis because my urethra is 1.5 inches long, right? Male urethra is on average 8 inches long, not the penis. I was not born yesterday, okay? The urethra all the way up to the urinary bladder, okay? Lower your expectations, ladies. And this, look at these bastards. Oh my God. Those have to go all the way down. They can break them up with sound waves, but then you're just going to have to pass a bunch of little bitty teeny ones. Bing, 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 into the toilet. Huh?
What's the scale of that?
Well, I have seen I don't know how big those are, but I've got some in my office because my students bring me all kinds of weird crap. I've got one that fit all the way. It was like the size of a renal pelvis. Yeah. And there was,
You don't.
well,
That part's stretchy.
Yeah, but
it is stretchy.
ouch.
They blast them up with sound, or it tears on the way down. There's a lot of bleeding potentially involved on the way down. So let's briefly talk about how you avoid these bastards because nobody wants them. Well, the conditions leading to formation, you could have a parathyroid problem that increased the amount of calcium. Too much soda. Soda is really, really nasty on your kidneys, especially diet soda. Ingestion of excessive mineral salts, abnormally alkaline or acid urine over time. Decreased fluid intake is one of the big ones. So if you really want kidney stones, don't drink very much except diet soda. That'll get you some kidney stones. And the prevention, drink lots of fluids, especially at bedtime. Why at bedtime? Because those minerals just sit in the calyces and the pelvis overnight, and they will be more likely to crystallize if they just sit there. And don't limit your good ions. Don't limit calcium, even though it leads to these, but do limit the things that calcium is bound to. And then we won't talk about dialysis because we've already talked about it. Okay, so let's take a few minutes. And we are going to, here's what I'm going to do with this quiz. Some of you guys have already taken it, but make sure you got all the answers right, okay? If you don't have time to do it all, like type them all in, write down the answer so that when I start it again at home, you can fix it. Does that make sense? Okay? You can't click in right now because I have to make it unavailable to you in order to present it in class. Then I'll make it re-available to you until tomorrow at 5. Okay? You ready? Okay. Okay, we're going to do this together. Everybody's going to get 100. Okay? So reabsorption, guys, occurs from what structure anatomically to what structure? Can you do it? Reabsorption doesn't occur from the glomerulus. It occurs from the tubule.
Oh, reabsorption.
Yeah, reabsorption occurs from the tubule into the peritubular capillaries. Does that make sense? Now, this could have also been vasorecta, but it had to be tube and blood, right? Right? Does that make sense? Yeah, tube and blood. Okay, everybody click in. Is it not letting you click in? C. Are you guys all clicked in? Everybody's in? Oh, you guys are fast compared to the other class. Okay, let's see if you made 100. Just made 100? Oh my gosh, good job. Okay. The myogenic regulation response in the kidney. Ready? Remember that one? That's the regional response in the kidney in response to low systemic blood pressure. Have you guys already clicked in? Oh, you guys have already done it. Okay, you can do it again if you got it wrong. Okay? Is to what? Do dilate, which one? Afferent arterioles. Everybody good? Afferent arterioles. Okay, cool. 18, 19 of you. Okay, ready for the next one? Okay. I don't want to wait for you guys to type this in. So if you haven't already typed it in, just scribble it down, okay? Filtration at the nephron occurs from what anatomical structure to what anatomical structure? Glomerulus to Bowman's capsule or the glomerular capsule. Okay? Everybody good? Okay. Which of the following are actively reabsorbed at the PCT? Do you know? Actively reabsorbed. It's A and B. Chloride is passive. Yes, it follows. Yeah. Proximal convoluted tubule. Proximal convoluted tubule. Everybody good? Okay, next one. Aldosterone. Use the terms correctly. Aldosterone causes sodium what? Reabsorption and potassium secretion. Yes? Okay. Do you hear how important it is to understand filtration, reabsorption, and secretion and how to use them? Because you will flunk that part of the test if you don't get those terms down. So don't do that. Okay. What triggers the release of renin? We've learned it like 3 times now. Low afferent arterial pressure. Got it? Okay. Okay. I'm going to let you guys think about this one. Think about it. Everybody good? One more person. Okay, what's the answer? The answer is B. Make sure you got it right before I click over. B, loop of Henle, yes. Okay. You should be able to do this one. It's been the same since the beginning of the semester. Glucose is primarily reabsorbed by blank blank transport. Secondary active transport using what kind of proteins? Carrier. Yeah. So if you didn't get that typed in, just write it down so that we can get all 10 done. What? Go ahead.
So in the notes it mentioned that it was co-transport, but I mean that's...
Oh, co-transport just means sodium and glucose are moving the same direction. Yeah. Secondary active transport. What?
You have to think of like your favorite cookies, a little bit of sweet, a little bit of
Exactly. Oh, yeah, I like those dark chocolate salted cookies. Okay. Okay, get this one right. In order for water to be reabsorbed at the distal convoluted tubule, what must be present? ADH must be present. Yes. Good. Okay. And regulated reabsorption of sodium at the DCT occurs under the influence of what hormone? Aldosterone. Yeah, got it. Good. Did you get 100? Okay. I will post that worksheet for you. Huh? I will post that worksheet for you in just a few minutes, and you guys can practice with that if you want to. Okay, Wednesday, see you for your test.